Last time we had been looking at problems involving electrocyclic reactions. We are continuing to look at more problems involving electrocyclic reactions. Let us look at our first problem. When we look at the thermal reaction, we get two products A and B. When we look at the photochemical reaction, we get two products C and D. When we look at these products, what we find, these products are all products A, B, C, D, tetracyclic with 3 double bonds. Our starting material is tricyclic and has 4 double bonds. Our product is tetracyclic with 3 double bonds. So you are going from n pi to n minus 1 pi. Therefore, it is an electrocyclic reaction. Okay. If I look at this reaction, then this is a 6-electron reaction. 6-electron thermal reaction is going to be disrotatory. Sorry, I am sorry. Okay. So I am looking at this 6-electron reaction. Thermal reaction is going to be disrotatory. This is also 6-electron reaction. This is photochemical. This is going to be conrotated. Okay. When I look at this, what am I looking at? When I look at this, my methyl group is on the inside, my hydrogen is also on the inside. So that's your starting material. Your 6-electron thermal reaction is going to be disrotatory. Therefore, your thumbs will move in opposite direction. Therefore, you will get one product in which both are below. In the other product, you will get both are up. So, that is your 10 position, that is your 9 position. C10 methyl, C9 hydrogen, both above. Second product, C10 methyl, C9 hydrogen. Both below. Okay. Now we look at the photochemical picture. Once again, your methyl group is inside, your hydrogen is also inside. Now it's a 6-electron photochemical reaction is going to be con-rotatory. So if I move it clockwise, methyl group will be below, hydrogen will be above. If I move it in the other direction, methyl will be above, hydrogen will be below. C10 methyl above, C9 hydrogen below. C10 methyl alpha, C9 hydrogen beta. What is our principle? In the thermal reaction, you are always going from less stable to more stable. Why is this more stable? It has more number of sigma bonds, therefore is going to be more stable. In your photochemical reaction, what is the principle? You are going from more conjugated to less conjugated. Your starting material has 3 conjugated double bonds. Your product has got 2 conjugated. So that's the picture. This is the compound called as precalciferol. And this is the compound called as lumisterol. Okay. So this is an example in which our starting compound is optically active. All the 4 products are also going to be optically active. Okay. So, yes, 1 second. 4-electron thermal reaction is going to be con-rotatory, photochemical reaction dis-rotatory. 4q plus 2 is the opposite. Okay. So that's, yes, some problem?
Sir, ABCD should have 3 double bonds.
Yes?
You said ABCD should have 3 double bonds.
I am not writing this, no? My starting material I said has 4 double bonds. Okay, all right. Okay. So that's 4 different products depending on where you are starting. Okay. Let's look at our next example. Okay. One is we have to suggest a mechanism for this reaction. And second is you have to give the stereochemistry of this product. if I look, my starting material has 2 rings and 2 double bonds, my product has 2 rings and 2 double bonds. So, there is no change in number of double bonds, no change in number of rings. So, apparently it looks like sigmatropic. But what do we find? A is an intermediate in this reaction, and A has 1 ring and 3 double bonds. So, obviously, you are going from 2 double bonds to 3 double bonds. So, you are doing electrocyclic ring opening reaction, and that is going to be a 4-electron process. And then obviously, this is again 3 double bonds going to 2 double bonds. So, that is going to be electrocyclic ring forming reaction. Okay. So, we have to identify what is that product which we are getting in this reaction. So, our starting material has 2 hydrogen cis. Obviously, it is a 4-electron reaction, that is going to be thermal reaction, therefore, is going to be con-rotatory. So, 1 hydrogen will be on the inside, 1 hydrogen will be on the outside. So, 1 hydrogen is on the inside, 1 hydrogen is on the outside. Okay. So, that is your 1, 2, 3, 4, 5, 6, that is your triene. How many total double bonds? 3 double bonds in a 10-membered ring. So, that is going to be your 1, 3, 5 cyclodecatriene. And what do we see? This is cis, sorry, this is trans, this is cis, this is cis. Okay. Now, our next reaction is again electrocyclic ring forming reaction. But now what we are going to have? We are going to have a 6-electron thermal reaction. There is no question of getting 4-electron reaction, because in a thermal reaction you have to go from less stable to more stable. So, you are going to have now 6-electron thermal reaction. All right. So, if you are looking at that 6-electron thermal reaction, what is our picture? 1 hydrogen is on the inside, 1 hydrogen is on the outside. 6-electron thermal reaction is going to be disrotatory. Therefore, your 2 hydrogens will be trans. So, if your first hydrogen is above, your second hydrogen will be below. When I did this reaction, I could have a second picture that we can see. What is it? My 2 hydrogens in my starting material were cis. I am going to do con-rotatory. What did I do? I moved both of them clockwise. But what happens if I move both of them anti-clockwise? Then what will happen? This hydrogen will be outside, this hydrogen will be inside. Okay. So, this hydrogen is outside, this hydrogen is inside. 10, 9, 1, 2. Now what's the problem? Now the middle double bond has become trans double bond. So I cannot form a 6-membered ring. The two ends are too far apart. So all that will happen is it will come here, it cannot go, this goes further, but this cannot go further. All it can do is it can go back. Goes here, small amount comes back, this small amount goes here. Then small amount again goes here, so finally you end up in this. So though the reaction looks as though it is sigmatropic, actually it involves two electrocyclic reactions. The first reaction is a 4-electron ring opening reaction. Your second reaction is a 6-electron electrocyclic ring forming reaction, which is going to be disrotatory. So that's an interesting example which looks in this fashion. Okay. Heat in the presence of water. What does that water do? It forms a hydrogen bond with the bromine, it weakens the carbon bromine bond and creates slight positive charge on this center. Okay. When it creates this slight positive charge on the center, what is our next product? Our product, we are going from cyclopropyl cation, we are going to go to an allyl cation. Please note, it is not a completely free cation. You are slowly polarizing carbon bromine bond. So you are not losing the stereochemistry. All right. This bond is weakening and we are getting ready to do this reaction. Okay. How many electrons are involved? 2 electrons are involved in the carbon-carbon bond and no electron is involved in the carbon-bromine bond. So it is a 2-electron system. If it is a 2-electron system, it falls into this category where Q is equal to 0. So the 2-electron thermal reaction is going to be disrotatory. Okay. So now that's your bromine, that's your methyl group, that's your hydrogens, and we are going to open this. When I open this, I am going to move this one in clockwise manner. This will therefore move in anti-clockwise manner, and I will get this intermediate. What is the problem in this intermediate? The two methyl groups are having serious problem with them. If I open it in the other disrotatory fashion, I move this one clockwise, this one will move anti-clockwise, and my two methyl groups will go on the outside. So, first type of opening will give me two methyl groups on the inside. What have we done? We have converted it into allyl cation. And when I do the other process, I will get this. And our expectation is this should be hindered, therefore, this process should be favored. But when I actually do the reaction, this is the favored process. So, let us look at this again, all right. When I do this, what is it I want you to see? This orbital and this orbital are downwards. Okay, so I will show those orbitals. And your polarized carbon bromine bond is upwards. When I do the other process, what do I see? These orbitals are upwards on the same side as the carbon bromine bond. Now, can you tell me why this process is favored, not this process? Sterically, as everybody said, this is more hindered and this is less hindered. But can you tell why this is the preferred process? This is like your anti-elimination, okay? Your this orbital and the orbital of the carbon bromine bond are on opposite sides, whereas this process is equivalent to syn elimination, anti-elimination with orbitals on the opposite side. What is happening? Now, this orbital can attack from the back side and displace this. So, not only is it disrotatory, but disrotatory in such a fashion that the newly formed orbital should be on the opposite side of the carbon bromine bond. Okay? So, this is the Woodward-Hoffmann again. Not only is it disrotatory, but orbital should be on the opposite side of the carbon bromine bond. Okay? All right. So, let us write that product. So, if I write this product, now water will act as a nucleophile, what is to be seen? The two hydrogens in the double bond are cis. If this was the product, the two hydrogens in the product should have been trans. The product has the two hydrogens cis. Therefore, not only is the reaction disrotatory, but my orbital should be on the opposite side of the carbon-bromine bond. I once again want to stress, if I make a completely free cation, I do this, now one p orbital is here, one p orbital is here, there is no stereochemistry left. So, what we are saying, this bond is getting weakened, but it is not a free cation, all right. So, bromine is on the upper face, therefore, your orbitals are on the lower face. Okay. All right. Now, let us look at the in the first starting material, all substituents were on the upper face. The methyls were on the upper face, the bromine was on the upper face. In my second case, my methyls are on the lower face, my bromine is on the upper face. In heating in the presence of water, what is the role of water? First, it polarizes the carbon-bromine bond and creates small positive charge on that carbon, not a completely positive charge, a small positive charge. Okay. Then what did we say? We must make this disrotatory and orbital should be on opposite sides of the carbon-bromine bond. When I do this now, my methyl groups are going to be on the outside. Hydrogen and I complete this, attack it. Water now is second role, first role helping to polarize the carbon-bromine bond, second role it acts as the nucleophile and gives you the corresponding alcohol. What's the systematic name you will give to this product? Should I start the numbering from here? Should I start the numbering from here? That's the question. From where should I start the numbering? I must start the numbering from the right hand side. Why should I start from the right hand side? So that OH will have the smaller number. So, 3-pentene 2-ol. In this case, the product is going to be, the trans product In this case, the product is going to be the cis product. Starting with this, I get cis product. Therefore, reaction is not only disrotatory, but the new orbitals of the carbon-carbon bond should be on opposite side of the carbon-bromine bond. So, confirmed by the structure of the two products. Starting with this, I get double bond cis. Starting with this, I get double bond trans. So, steric is not the factor that governs. Factor that governs is the orbital should be on opposite side of the carbon-bromine bond. Okay. So, that is the interesting reaction that we have seen here. Okay. Which reaction will proceed faster? Obviously, in this transition state, methyls are having hindrance, whereas in this transition state, methyls are not having hindrance. So, this reaction should be fast, that reaction will be comparatively slow. Okay. All right. Support for this comes from this experiment. If I compare the rates of reaction of this, relative rates, what do I find? Relative rates of reaction 1, 4, 40,000. Here metals are on opposite side of the tosylate group. Therefore, it corresponds to this system. Your that's going to be your intermediate. When metals are on the same side, that's going to be your intermediate. And what do we see? This reacts 10,000 times faster than this. So, that is very easy to understand. C reacts faster than B by 10,000 times. Okay. What is the intermediate in case of A? In case of A, that will be the intermediate. What is our expectation? Here metals are having problem, here hydrogens are having problem. Therefore, this should react faster than this. But what is the observation? Observation is this is reacting 4 times faster than this. Why? I will localize this. Now can you tell me why? That's a primary cation. That's a secondary cation. Secondary cations are more stable than primary cations. Number 2, this double bond is mono-substituted. This double bond is di-substituted. So, cation is secondary, double bond is more substituted. So, in spite of the greater steric hindrance, this compound reacts faster than the one without metals. Okay. All right. Let's look at our next example. Okay. All right. What have we shown? That's our 6-membered ring. That's your 3-membered ring. Your hydrogens are below. Your ring is on the upper side. When I put the chlorine like this, what does it mean? Chlorine is endo. If I put the chlorine like this, chlorine is exo. If I start with the endochlorine, I get this product, heating at 125 degrees. 210 degrees, there is no reaction. Okay. So, when I do this, what is my picture? My hydrogens and chlorine are on opposite sides. So, when my hydrogen and chlorine are on opposite sides, sorry, I'm sorry. Your hydrogens are below and your chlorines are on the same side as your R groups. Okay. So, what happens when I do this? That's the intermediate. The alkyl groups are on the inside. When I do this, methyl groups are on the opposite side of the chlorine. So, let us put it like this. That will be the intermediate. All right. In this case, the methyl groups will be on the inside. In that case, the methyl groups are on the outside. If I join it, what is the meaning? One, two, three, 4, 5, 6, 7. It means that I have to create trans double bond in a 7-membered ring. And a trans double bond in a 7-membered ring is very, very unstable. So, only the endo halogen reacts. The exo halogen gives you trans double bond. Therefore, that does not react. Okay. So, starting with this, that is going to be the intermediate. Now, there is no nucleophile. Therefore, chlorine leaves in the first step. In the second step, it serves as the nucleophile. So, chloride leaves and chloride acts as the nucleophile. So, if your product is going to be double bond and adjacent to it is going to be your chlorine. Only when the halogen is endo, reaction takes place. When the halogen is exo, the intermediate will have trans double bond in a 7-membered ring. Therefore, there is no reaction. Okay. We observe the same picture here. (126°), 3 hours. Endo-chlorine reacts. Exochlorine, 250°, 4 hours. No reaction. What is the driving force for this reaction? We are going from the less stable cyclopropane ring to the more stable 6 or 7-membered ring. So, that is the picture that you see. Okay. All right. In order to confirm this, endo-tosylate reacts two million times faster than the exotosylate. The exotosylate, I treat it with acetic acid at 150°, 3 months, 90% of starting material is recovered. in the endo tosylate at 126 degrees, I get product. Calculating number of collisions, it means that the endo tosylate reacts 2 million times faster than the exotosylate. Okay. So, in the first case, we were only considering opening of the side cyclopropane ring, but here cyclopropane ring is attached to another ring. So, when it opens, you build up a 6-membered or 7-membered ring, and trans double bond in 6-membered or 7-membered ring is impossible. Okay. Let us look at another example. Heat it in the presence of water. Now, I get product. Why do I get product? Now, when I open it, my ring is going to be 8-membered. Trans double bond in 8-membered ring is unstable, but our starting material has a cyclopropane ring. So, starting material is more unstable, product is less unstable. So, in the earlier case, it was trans double bond in 7-membered ring or 6-membered ring. That was extremely unstable in case of 7-membered, in case of 6-membered, impossible. So, I get product, but here one, two, three, 4, 5, 6, 7. That is the product. Water has again double role. First is it helps in polarizing carbon-bromine bond. In the next step, it serves as the nucleophile, and you end up in this. So, when 6 was joined to 3 or 5 was joined to 3, exo compound did not react. But when 7-membered ring was joined to 3, exo compound did react, because trans double bond in 8-membered ring is unstable, but not impossible. Okay. Let us look at our next example. All right. In one of the products, fluorine is endo. In the other product, bromine is endo. When I look at spectral properties, I cannot decide which compound has chlorine endo, which compound has bromine endo. Okay. So, we will use a different method to get this answer. Before this, let us look at this very famous reaction. Phenol reacts with chloroform in the presence of alkali. What is this famous reaction? That's the Reamer-Tiemann reaction. Okay, very good. All right. So, you get ortho and para hydroxybenzaldehyd. Okay. How does this reaction work? What's your first step? What's the first step in this? Yes? Carbene formation. How does carbene form? Okay. Chloroform hydrogen is acidic. So, you get this anion. Why is it acidic? The one factor is inductive effect of the chlorines. What's the other factor? How happy you are if I write this? All right, not all right. Our friend says no. Why no? It cannot form. Why it cannot form? Because you say so. Why is it cannot form? If that had been a nitrogen or an oxygen, it cannot form. Why? Because that atom has more than 8 electrons. But if that atom is chlorine, it can form. Why? Because chlorine has vacant d orbitals. Okay? So, one reason is the inductive effect of the 3 chlorines. The second is chlorine has vacant d orbitals. Okay. All right. When I have a ketone, I get the pi bond. Why? This is the pi bond involving p-p overlap. The two orbitals are parallel to each other. Therefore, your pi bond involves a p-p overlap. When I look at a d orbital, your d orbitals are in this shape. And now what is this? They are not perfectly parallel to each other. This we call as a p-p pi bond. This is a d-p pi bond. A p-p pi bond has orbitals parallel to each other. So, p-p pi bond is strong, a d-p pi bond is not strong. Okay. So, that is the first picture. The hydrogen is acidic because of the inductive effect. Carbanion is stabilized by inductive effect of 3 chlorines. It is also stabilized by resonance involving a weak dp pi bond. Okay. Step number 2. Cl minus goes off and you get dichlorocarbene. Okay. That is your dichlorocarbene. This carbene, is it an electrophile, is it a nucleophile? Why is it electrophilic? It is electrophilic because it has only 6 electrons, but our definition of a nucleophile is anything which has a lone pair. So, in that sense it has a lone pair. So, in principle it can be electrophile or nucleophile. When it acts as a nucleophile, what will happen? When this attacks, neutral carbon will become positive carbon. Okay? So, low tendency to attack as a nucleophile. How will I prove this? That carbene is an electrophile and not a nucleophile. If I compare rates of reaction, as I increase the alkyl groups on the double bond, what will happen? Double bond will become more nucleophilic and then carbene reacts faster to it. This establishes that carbene is an electrophile. Okay? That's okay. So, what happens with this electrophile? So, phenol is rich in electrons, so phenol attacks this. Therefore, we get this intermediate. Now, what is next step? I shift the hydrogen from here to here. And I make the negative charge. And this undergoes hydrolysis. Now, loses HCl to give you this. Okay. When I look at this, one rack structure which I can write for the carbene is this. Both electrons are in the same orbitals and electrons are paired. I call this as a singlet carbene. Alternatively, one electron can be in each orbital. Why did I write both of them with the same spin? When I wrote them in same orbital, I wrote them with opposite spin. When I wrote them in different orbitals, I wrote them with the same spin. This is obviously your triplet carbene. But why one time I wrote it paired, one time I wrote it like this? Pauli's principle says that when electrons are in the same orbital, they prefer to have opposite spin. And the very famous Hund's rule says that when electrons are in different orbitals, the preferred direction is in the same spin. Okay? So that's your singlet carbene and your triplet carbene. What's the proof that a carbene is a singlet carbene or a triplet carbene? Some carbenes are singlet carbenes, some carbenes are triplet carbene. If the carbene is a singlet carbene, if I start with cis 2-butene, I get only cis product. If I start with trans 2-butene, I get only trans product. So singlet carbene reaction is stereospecific. In a triplet carbene, reaction is not stereospecific. All right? Okay. We'll have a little break and come back. Diversion, we come back to this. Okay. So we take this, treat with OH minus. So following the same logic, first step will be formation of this anion. Will Cl minus go off or will Br minus go off? Why Br minus? Yes? Br minus goes off because the product tells you that Br has gone off. Why this, not this? Which is better? Cl minus is better or Br minus is better?
Dispersal of charge is more in Br minus. Dispersal of charge, hence it is stable.
What I was trying to say is, since Cl is more electronegative, Cl minus is in principle better than Br minus. But what we have to see is, when I break the bond, the carbon-bromine bond is weaker than the carbon-chlorine bond. Or in another language, Br minus is a better leaving group than Cl minus. Even in nucleophilic substitution, reaction of RBr is faster than reaction of RCl. Okay. All right. Right. A gives you, on heating in presence of water, A gives you chloroalcohol, B gives you bromoalcohol. Which is A, which is B? What did we say earlier? In all of these reactions, endo halogen leaves. So, this is chlorine so chlorine will leave, you will get this cation, and now this cation will be attacked by water. So, the one that gives you bromoalcohol must be chlorine endo, and the one that gives you chloroalcohol must have bromine endo. When you get the product, unfortunately product does not tell me I am chloroalcohol, all right. You have to find out which is chloroalcohol, which is bromoalcohol. So, how will you do that? You got some product, how will you prove it is chloroalcohol or bromoalcohol? What do you do in mixture separation? Yes. What's the thing? Practical lab is there, right? Theory lab has got nothing to do with practical lab. If I add silver nitrate, what happens? Chloro compound gives you white precipitate, bromo compound gives you yellow precipitate. If I add will this compound give you yellow precipitate? What do we do in sodium fusion? We add sodium. What is that sodium doing? It is converting covalent carbon hydrogen bond into sodium chloride or sodium bromide. So, the test is a test only of ionic chlorine or ionic bromine. If you do not do sodium fusion and you simply add silver nitrate, no precipitate will be formed. Okay. So, when I do that sodium fusion, I am converting covalent chlorine into sodium chloride, and sodium chloride is giving you white precipitate with silver nitrate. So, the test is for ionic chlorine or ionic bromine. It is not a test for covalent chlorine. Okay. All right. What is the moral of this long story? When you do practicals, ask questions to yourself, why am I doing this? All right. Take flask, heat, add 100 ml, take 250 cc round bottom. Why 200? Why round bottom? These are the questions you should ask yourself. Okay. And this is last chance in your life when you can ask this question. If you go to industry and says, sir, why round bottom? I want to use flat bottom. He will say, go home. All right. Okay. So, ask all these questions, don't do practicals blindly. Okay. All. So, let us look at our next example. Just like in the previous example, when I use this, I will get two products. One will have fluorine towards the ring, other will have chlorine like this. In one case, fluorine will be endo, in one case, chlorine will be endo. What should I use to generate this carbene? Should I use this? Should I use this? Or should I use this? Sorry. If I use this, now what I want? I want bromine to leave, and bromine leaving is very easy. So, I will use this. If I use this, I will get difluorocarbene, not fluorochlorocarbene. If I use this, I have to break carbon-chlorine bond. Here I have to break carbon-bromine bond. Okay. All right. So, in one case you have fluorine endo, in the other case you have chlorine endo. So, fluorine endo fluorine will leave, and since there is no other nucleophile, you will get and now F minus, which went out in first step, will act as the nucleophile. So, you will get this product. If I start with the chlorine endo, I will get this product. In this example, one way to find out whether I got bromoalcohol or chloroalcohol is to do that silver nitrate after sodium fusion. But the better method is determine molecular weight. The bromoalcohol will have much higher molecular weight than chloroalcohol. Okay. But in this case, molecular weight is the same and both compounds contain fluorine and chlorine. So, how will you know which is which? I look at the proton NMR of this compound, what will I see? I look at the proton NMR of this compound. Yes? Yes. Fluorine has spin equal to 1/2. So, in this case, you will see hydrogen coupling with fluorine, hydrogen will also couple with this hydrogen. In this case, hydrogen will couple only with that hydrogen. Fluorine has spin equal to 1/2, so fluorine will couple with hydrogen. Fluorine doesn't have spin 1/2, it will not get involved in coupling. So, your NMR spectrum will help you to get the answer to this. All right. AR is equal to paramethoxyphenyl and E is the ester. All right. If I take one and heat it at 100 degrees, I will get mixture of 1 and 2. So, that is the first question. How does this happen? What is the first point you have to see? This is a 2-electron system and now nitrogen has a lone pair. So, this system is now a 4-electron system. The earlier examples were allyl cation, 2-electron system. This is now an example of a 4-electron system. Okay. So, your 4-electron system is going to open up. What can you see of this 4-electron system? What will happen? Your starting ester has the 2 ester groups cis. It is a 4-electron system. Reaction is a thermal reaction. Therefore, it is going to be con-rotatory. So, one ester group will be inside, one ester group will be outside. What is stabilizing negative charge? Negative charge is stabilized by resonance. What is stabilizing positive charge? That's a donor, it will push electrons, push it here, I can get plus charge at that point. Okay. So I get this. One ester group is inside, one ester group is outside. One ester group is inside, one ester group is outside. So if it undergoes cyclization, what should happen? Again it should be conrotatory, alright. So one ester group is inside, one ester group is outside. What should happen? Both esters should be down or both esters should be up. So comes here, comes here. If I start with this, one ester is up, one ester is down. Make it conrotatory, what will happen? Both will be inside, that will have lot of problem. So it will prefer to be both ester groups outside. So what is expected? 1 should give you 1A, 2 should give you 2A. When 2A goes back, it will give you 2. When 1A goes back, it will give 1. And we said in an earlier example, even if you do 2 million collisions, conrotatory, 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 it never becomes disrotatory. So how does 1A go to 2? What is the picture now? This has become, this bond can rotate. It is now a single bond. If it is a single bond, I can rotate this. When I will rotate this, let me write it like this, probably you will see it better. Rotate this, what will happen? Ester group will go outside. So I can convert this into this, because this has a single bond character, I can rotate around the single bond. So it opens up, there is no disrotatory mistake. There is a single bond character to it, so I can convert 1A into 2A. Automatically 2A can go this. So 1 on heating gives you mixture of 1 plus 2, 2 on heating gives you mixture of 1 plus 2. Okay. If I heat this, in presence of acetylene dicarboxylate, my starting material has 1 double bond, the other starting material has 2 double bonds. My product is cyclic with 1 double bond. So one of my starting materials has 1 double bond, other starting material has 2 double bonds, total double bonds 3. And in my product, there is only 1. So the reaction that is taking place is a cycloaddition reaction. Okay. So my two esters were cis in number 1. In the product, my two esters are trans. If I start with compound 2, in the product, my two esters are cis. When I heat one alone, I get mixture of 1 plus 2. When I heat one in the presence of acetylene dicarboxylate, 1 gives you only 3, 2 gives me only 4. So, how do I explain this? When I do this addition, this reaction is very fast. So, K3 is much faster than K1. Before it undergoes bond rotation, it undergoes cycloaddition. Therefore, starting with 1, I get single product 3. If I start with 2, I get single product 4. If I do not have acetylene dicarboxylate, that anion has sufficient time to undergo rotation. Therefore, starting with 1, I end up in a mixture of 1 plus 2. So, in the presence of acetylene dicarboxylate, the reaction is 100% stereospecific. All right. Okay. Look at this, look at this. When I look at this, what do I see? I get this. And then what did we say? Positive charge is stabilized by aromatic ring, and negative charge is stabilized by ester. So, here also positive charge is stabilized by aromatic ring, negative charge is going to be stabilized by carbonyl. Answer is no reaction. Why no reaction? Both my ester groups were on the same side. So, when I do 4-electron reaction, what should happen? One should be inside, one should be outside. When I say inside, what does it mean? What is this? It is again trans double bond in 6-membered ring. So, though electronically expected was, pattern is same, there is an electron donor on nitrogen, there is electron withdrawal, in first case ester, in the other case amide. But that is open chain, it reacts. That is cyclic. To react, it should give you trans double bond in 6-membered ring, and trans double bond in 6-membered ring does not take place. So, you heat it for any length of time, nothing happens. Let us look at our next example. I start with bicyclic compound with 3 pi bonds. 2 are carbon-carbon double bonds, 1 is carbon-oxygen double bond. In my product, I get tricyclic compound, and there are 1 carbon-carbon double bond, 1 carbon-oxygen double. So, I am going from n pi to n minus 1 pi. So, this is an electrocyclic ring forming reaction. Okay. All right. So, what does that H3PO4 do? What is H3PO4? Is phosphoric acid. So, what do acids do? Acid should protonate. So, first step should be protonation. So, oxygen lone pair gets protonated. Which resonance form is more important? Oxygen plus or carbon plus? Carbon plus. That was the very much expected wrong answer. Why is it wrong? Immediate reaction is carbon plus is better than oxygen plus, because oxygen is more electronegative than carbon. But when I look at this structure, this has only 6 electrons. Here all atoms have complete octets. So, this resonance structure is much better than that resonance structure. Okay? All right. This oxygen is not a very strong base, and phosphoric acid is not a very, very strong acid. So, protonation takes place only to small extent. All right. All right. So, to small extent it gives this, to still smaller extent it gives this. But moment it gives this, now what do I see? This has become pentadienyl cation. How many electrons are there? 2 electrons in this double bond, 2 electrons in this double bond, no electrons in the positive charge. So, it is a 4-electron thermal reaction. 4-electron thermal reaction is going to be conrotatory. Okay. So, you do that 4-electron thermal reaction. That is a methyl group, that is a methyl group. So, your two methyl groups are on the inside, it is a 4-electron thermal reaction. Therefore, it is conrotatory, one methyl group should be up, one methyl group should be down. Let us show it like this. One methyl group should be up, one methyl group should be down. So, pentadienyl cation has converted into cyclopentyl cation, cyclopentenyl cation. Okay. So, now what will happen? This is the enol form, will go to ketone, and this positive charge will be stabilized. How will it be stabilized? By loss of a hydrogen. So, that is going to be the product. So, this is an example of the reaction of a, earlier today we saw reactions of allyl cations, then that example was a reaction of a 4-electron system equivalent to allyl anion. This is our first example of the reaction of a pentadienyl cation. Okay. Let us look at our next example. In our very first lecture, we said that pericyclic reactions do not involve acid or base. Then you will say that, see, you are involving acid. What is the role of the acid? Our reacting species is this. So, its role is to create starting material. This is the starting material for the pericyclic reaction. So, acid is involved to prepare the starting material. Okay, that is what we see there. All right. You get two products, A is major, B is minor. Both are tricyclic enones. All right. Your starting material is bicyclic with 3 double bonds, product is tricyclic with 2 double bonds. Therefore, it is an electrocyclic ring forming reaction. First step is once again protonation. To a small extent, this will give this. Okay. So, both our hydrogens are on the inside. What is now the difference? The first example was 4-electron thermal reaction, therefore, it was conrotatory. This reaction is 4-electron photochemical reaction, so it is going to be disrotatory. My two hydrogens are on the inside, In my product, the 2 hydrogens will be cis. Let's do this. Okay. One is this OH will be converted into ketone. Enol will go to ketone. Why do we get 2 products? I can stabilize this by losing this proton, or I can stabilize this by losing that proton. Which will be the major product, left hand side or right hand side? Left hand side, why? It is the more substituted olefin. It is tetra substituted, whereas the right hand side has only 3 substituents, 1, 2, 3. So that is the major product, this is the minor product. From the stereochemistry point of view, major product doesn't tell us anything, because now we don't see the stereochemistry. In the minor product, we are seeing that the 2 hydrogens are cis, and that told us that it's a 4-electron photochemical reaction, and therefore it's going to be disrotatory. Let's look at our next example. Intermediate A is tricyclic with 3 pi bonds, 1 positive, 1 negative charge. How many double bonds are there in starting material? There are 4 double bonds, and my product has only 3 double bonds. Therefore, it's an electrocyclic ring forming reaction. What is the difference between this and that? This now is a 6-electron system. It's not a pentadienyl cation, but it's the equivalent of a pentadienyl anion. Okay. So 6-electron reaction. If it's a 6-electron reaction, what is the question that we have to ask? Your R is on the inside, your hydrogen is also on the inside. So, both your substituents hydrogen and R are on the inside. It is a 6-electron reaction. 6-electron reaction is going to be photochemical, it is going to be conrotatory. So, both groups are on opposite sides. You are not in a position to isolate this. Look at your starting material, neutral compound, aromatic, therefore very stable. Look at this intermediate, we have gone from aromatic to non-aromatic, and it has one positive charge, one negative charge. So, we have gone from a very stable system into an unstable system. In a photochemical reaction, the important point is you go from more conjugated to less conjugated. Okay. All right. You go to a tricyclic compound with 3 pi bonds and no charge. Your starting material has 3 pi bonds and 3 rings, your product has got 3 pi bonds and 3 rings. So, this is an example of a sigmatropic reaction. Okay. How many electrons are involved in this? 2 electrons in this, 2 electrons in this, 2 electrons in this. So, it is a 6-electron sigmatropic reaction. Hydrogen is, I am breaking the bond between 1 and 1 dashed, I am forming the bond between 4 and 1 dashed. It is a 1,4 sigmatropic hydrogen migration in an anion. 1,4 sigmatropic hydrogen migration in an anion. 6-electron hydrogen migrations take place with retention. So, your hydrogen was below, in the product your hydrogen is below. Okay. So, that is the first step. You are going from very stable aromatic system to a non-aromatic system. That is why you can't do it thermally, you have to do it photochemically. And your second step, you go from unstable non-aromatic system back again into stable aromatic system. That reaction is your thermal reaction. Okay. All right. Let us look at our next example. All right. Can you see that? What letter are we describing? W. So, it is in a W conformation. So, the attempt was you treat this with H plus, and what was expected? One should get this. What will we see? These two metals are same type, these two metals are same type, that will be the third type of metal. So, we will see three types of metals, and all metals in the NMR spectrum will be attached to sp2 carbons. So, all metals will be quite downfield. But when you look at the product, in the product you find that two metals are attached to saturated carbon. So, expected was the formation of this product. But what was seen in the NMR was product has two metals on saturated carbon. Okay. So, what are we going to do? Rotate around this single bond, rotate around this single bond. What have we done? We have converted W conformation into C conformation. W conformation has become C conformation. And what is this now? This is a pentadienyl cation. So, first okay. So, what do we get? That is a secondary cation. But in the NMR spectrum, what we saw? Only two metals are attached to saturated carbon. Here we have four metals attached to saturated. So, something must happen to this. What type of cation is this? Allylic and secondary. So, we migrate the metal. When we migrate the metal, what do we get? We get a tertiary cation. Now, still we have two metals attached to saturated carbon. This metal will be doublet in the NMR spectrum. Why doublet? Because there is a hydrogen here. So, what do? We move that double bond. Now what? Two metals are attached to saturated carbon. All these metals are attached to sp2 carbons. And of course, positive charge can be at this carbon or positive charge can be at this carbon. So, the attempt was to see the NMR spectrum of this. The product that we got, NMR spectrum is this. This was the work done by George Olah. He wanted to study the NMR spectra of cations. He tried to prepare that cation, he ended up in a totally different cation. Okay. When we meet next time, we will take this further.